I'm Roberto Jordaney, and today I'm going to talk about the problem of concept drift in malware classification models. This work is done with a collaboration of my colleagues Sharad, Wang, Papini, Nouretdinov, and with my supervisor Lorenzo, Cavallaro. So what is classification? Usually classification is a two-phase process where in the first phase you build a model with known objects that have a label. And in the second phase you use this model to predict the label for the object unknown, the object that you don't know the label. The objects are usually described as a vector or feature, and this feature can be anything that describes as best as possible the object itself. Here we have an example. We have two sets of objects. On the left-hand side we have the Pikachu, and on the right-hand side we have the Charmander. This object can be described with the color, with the shape, and training the model means we want to separate the feature space in such a way that all the objects with the same label will be grouped together. So in this example will be done with this line. So on the left we will have all the Pikachu, and on the right we will have all the Charmander. So what happens when we need to classify new objects such as this one? So on the top right we have Raichu, that is an evolution of Pikachu. On down we have Charmeleon, that is an evolution of Charmander, and we have also a totally new family that is Hitmonlee. These objects have a property that the model doesn't know at all, new properties that are statistically very different from the previous one, from the model, from the object, from the statistical property that the model knows. So it will be likely that the model will make wrong prediction when try to predict this object. In fact, wherever you place Hitmonlee, that is the new family, it will be wrong. In this case, it is classified as a Pikachu, but it's wrong. And Charmeleon, for instance, is classified correct because it's an evolution of Charmander, but this can be also a lucky guess. So, of course, this problem exists also in multi-class classification, because if you add a new family, for instance, a new family of Pokemon, the Hitmonlee will be always classified wrongly wherever you place this Pokemon. So this is the problem of concept drift, and it will occur in non-stationary contexts. What does it mean? It means that it will appear when the model is static and the object that you are trying to predict are dynamic, so they change over time. In malware classification, this is due to malware evolution, because the malware evolved in order to evade the classifier, and also when a new family will appear that is totally new, that it was not known before. So what we want to do, we want to assess the prediction that a model is doing, or the prediction of a classifier, and we try to do in an algorithmic agnostic way. And doing that, we try to identify then concept drift. So our contribution is conformal evaluator. That is a framework that enables you to statistically evaluate the prediction made by a machine learning classifier. And we also identify per class threshold that will enable us to mark a prediction made by a classifier as reliable or unreliable. So our proposed solution, conformal evaluator. So again, conformal evaluator will mark each decision made by a classifier as reliable or unreliable. It builds and makes use of p-values. So conformal evaluator will build p-value and will make use this p-value as an assessment criteria. And based on this p-value, we will compute per class threshold that will enable us to identify unreliable prediction. So why p-value? What is a p-value? So p-value will measure how well a sample fits into a class, and it will represent the number of training elements that are more dissimilar respect to the element that we are trying to predict. So we use the word non-conformity score because we want a number that is higher when the object that we are trying to classify is more dissimilar than a group of objects. But to understand a bit better what is a p-value, let's make an example. So the machine learning classifier that in this example that we will use is the distance from centroid. So a new object will be classified to the class that is closer to the centroid. So in this setting, we have three classes: the red square, the triangle, the green triangle, and the blue circles. And now we are trying to calculate the p-value for the new test object, that is the star object. So what we do is we compute the distance from the centroid that is represented with the cross. And then we count how many objects are more dissimilar. So in this case, more dissimilar means that we need to count how many objects are outside the circle that I'm showing you. So in this case, will be 9 objects outside the circles. And the p-value for the test object for the blue class, for the blue circle class, will be 9/10. 10 is the total number of objects in that class. We will do the same for the green triangle class. In this case, it will be 4/12. Again, this is 12 because the total number of objects in the green triangle class is 12. And also, for the red square class, that will be 0. This p-value represents the statistic support that we have when the classifier chooses that class. And we will use this. How do we use this? Let's see how conformal evaluator use and build these p-values. So, conformal evaluator extract the non-conformity measure from the underlying machine learning algorithm. So, the non-conformity measure can be any function that measures the distance from an object to a group of objects. And therefore, our framework is very generic because a lot of functions can produce these numbers. We will use this non-conformity measure to produce score that will be used in the p-value computation. In the previous example, the non-conformity measure was the distance from the centroid. Other examples of non-conformity measure are the distance from the hyperplane, when we talk about the SVM classifier, or the random forest probability. Again, the probability is a conformity measure because it's higher when is a number that is higher when there is more chance that the object is belonging to a group of objects. So we change the sign when we have conformity scores. So now that we have extracted the non-conformity measure, we build p-value for all training samples for all the classes. And we do this in a cross-validation fashion. Then, with all this p-value for all the classes for all the training sample, we are going to compute the threshold for each class. Of course, here we are using only the training data set that we have, because of course we don't know what will be the test data set. So how we identify the class threshold, how we compute the per class thresholds. So we can define two constraints in our threshold, and one is the desired performance that we want to achieve on the prediction that are marked as reliable. And the second constraint is the number of unreliable predictions that we are able to tolerate in our model. The second constraint, the number of unreliable predictions, we added this constraint because when a model will make a prediction that will be marked as unreliable, usually there will be another phase, an additional phase that will investigate, that will manually investigate these samples. So therefore, we added this constraint to model also this behavior. And we assume in this case that the performance of non-drifted elements will be similar to the one that are declared by the algorithm. And the prediction that are made with high confidence by the classifier, we also have high p-values. So once we have defined the constraints for identifying the threshold, we can compute the threshold. And how we do that? For each class, we separate the correct decision and incorrect decision, and we compute all possible thresholds for that class. Then we keep the threshold that satisfy the constraints that we have defined, and we maximize all the thresholds that we have. We maximize one constraint or the other. So now we have understood how we identify the threshold for each class. So let's move on to some experimental results. So we have tried our framework on 2 case studies. One is binary classification case studies, is an Android malware detection, and we reproduce the Drabin dataset, the Drabin algorithm, and Drabin is an algorithm that was published in NDSS in 2014, and use static feature on Android application. Static feature as the permission, the API call, all the strings that that the algorithm finds inside the APK, such as URL as well. And as a decision-making function, it uses linear SVM, and we will use linear SVM as well as our non-conformity measure. And in this case, we will investigate the concept drift as the malware evolution. We also tried our conformally evaluator framework on a multi-class classification algorithm that was proposed to solve the Microsoft Kaggle competition in 2015. It was ranked one of the top algorithms. And for these case studies, we investigated a new malware family. So due to lack of time, I'm not going to talk about the multi-class classification, and I will focus on the binary case studies. So in our binary classification, we use 2 data sets. One is the Drabin dataset, the original Drabin dataset, that has sample collected from 2010 to 2012, and it has more than 100,000 benign application and more than 5,000 malware application. We also use the Marvin dataset. That was malware was an algorithm published in ComStack in 2015, and it has malware application collected from 2010 to 2014. Of course, we remove the duplicates, duplicate application that we find already existing in the Drabin dataset. So the Marvin dataset has application collected in an overlapping period of time of Drabin dataset, and also newer application. Therefore, we expect to see some drift in the data because application change, malware change, so we expect to see some drift. And the Marvin dataset has more than 9,000 benign and malicious application. So the first experiment that we have done is to confirm that we have a drift in the data. So we train a model with the Drabin dataset, and we test the model with 4,500 benign and malicious application from the Marvin dataset. So the results are on the confusion matrix here, and we can see that already from the confusion matrix, a lot of malicious application of the Marvin dataset are misclassified, are benign. And this is already a good sign that there is a drift in the data. But to further convince you that there is a drift in the data, I'm plotting the object, the training and the testing object. And of course, I'm plotting this in a two-dimensional space, but all these objects have more than 100,000 features. So I'm reducing this dimensionality with this NIT. That is an algorithm that tries to keep the distance in high-dimensional space also in low-dimensional space. So from the graph, we can see that the Marvin malicious applications that are the blue dots, some of them are already quite far from the Drabin malicious application that are the orange square. But if I add also the benign application coming from Drabin, you can see that also the malicious Marvin application that were not too far from the Drabin malicious application are now even closer to the benign application. So it's another sign that there is a drift in the data. So once we have confirmed that there is a drift in the data, we want to identify, we want to use our conformal evaluator to identify threshold in order to mark, in order to see if we can identify the unreliable prediction. So again, we use the same setting. We train a classifier with the Drabin dataset, and we test with 4,500 benign and malicious application coming from the Marvin dataset. And we use as a constraint for our conformal evaluator a F1 score of 0.99 and 0.76 of elements that are marked as reliable. So the results are here in this confusion matrix. And we can see that we identify, we mark as unreliable the prediction of more than 2,000 malicious samples that before were misclassified as benign, and also some benign applications that were correctly identified, more or less 200. And this is due to the fact that these applications are closer to the decision boundary. So now that we have identified the sample that were misclassified, we try to see if this new knowledge as an input for a new model is helpful. So what we do is we train a new model with the Drabin dataset and the sample that were marked as unreliable from the previous experiment. And then we test this new generated model with a new batch of 4,500 benign and malicious applications from the Marvin dataset. Of course, these two batches of samples, they don't overlap. And the results are here in this confusion matrix, and we can see that both precision and recall for both classes are actually very high. So the information, the element that were marked as unreliable bring a lot of information in the new generated model when they are labeled. So in this experiment, we ask ourselves if we can use other metrics to compute the threshold for identifying reliable or unreliable prediction. So the matrix that we compare is the probability, because probability is given as an output for almost every machine learning classifier. But p-value can also be computed for machine learning algorithms that do not provide probability. So we compare the central tendency and dispersion point of the true positive distribution when we train a model with the Drabin dataset and the test again with 4,500 benign and malicious application. So when we compare the first quartile of the true positive rate of the prediction that were marked as reliable from conformal evaluator using a p-value as approach, we can see that we have 90% of correct prediction. Instead, if we use the same approach, the same algorithm, but used with probability, this will drop down to 66%. Another important point is that the performance for the elements that are marked as unreliable Again, in this case, when we use conformal evaluator p-values, the prediction are 0, and the true positive rate is 0. And when we use a probability approach, the true positive rate is 0.31%. So again, this shows that the p-value are better suited. And why are better suited? Because probability needs to sum up to 1, while p-value do not. So if we have a case of concept drift, for instance, that a sample does not belong to any of the class of the model, the p-value, there will be a probability for one class that is skewed, that is high. So instead, for p-value, we don't have this problem because p-value don't have to sum up to 1. So to conclude, we propose a conformal evaluator that is a framework to assess the quality of the prediction made by machine learning classifier, and we identify concept drift. The conformal evaluator framework is algorithmic agnostic and use as a non-conformity measure that is derived from the machine learning classifier. We build statistical support based on p-value, build again from the non-conformity measure that is again derived from the machine learning algorithm. And then we build threshold in order to identify reliable or unreliable prediction. Then we use this framework to evaluate two use cases, one on Android malware application and one on multi-class classification. And if you want more information on conformal evaluator code and dataset, you can visit s2lab.isg.rhul.ac.uk/project/CE. So thank you. If you have any question, please feel free to ask.
We have some time for questions. Please state your name and application before question.
Rachel Greenstadt, Drexel University. So I think this is really interesting work using an abstaining classifier for malware family identification. In work like this that's been applied to website fingerprinting or stylometry, they've evaluated a number of different p-thresholds, not just the straight-up p-value, but perhaps the gap confidence between the p-value for the top and the second, and other types of things. Did you look at any of those in your?
Yes, actually is one of the future work, because we can use, as you said, other metrics like what we can call algorithm confidence, so the difference between the highest p-value and the lowest p-value or something like this. And this is actually one of the future works, yes.
Okay. Yeah. I have a quick question, sir. First of all, so the Windows P binary have similar results. Is that right?
In the Windows case study, we evaluate a different scenario where we have a new family that pop up in the testing data set.
Okay, but the results show that
yes.
Similar trend, right? So in your case, you define the concept drift as the family evolution. Is that right?
Yes, in the binary case study, yeah.
Do you think there will be other cases so you potentially miss, or even in the family revolution there will be other exceptions that may not be?
Sorry, can you say it again?
So do you think in this case, concept drift equal to family evolution?
Yes, we think so, because the classifier is just a binary classifier, so it's identified in malware or benign application.
Yeah. Okay, David, question?
Hi, Dave Wagner from UC Berkeley. Great work, I loved it. When you're using the conformal evaluator to identify which points to retrain on, to add to your training set, it reminded me a bit of active learning, which also has a similar notion of identify samples where I'm not sure on and try to find a correct label. And I was wondering if you could comment at all on how this compares to other techniques for active learning, and if that's the way you think of it or what the relationship is.
Sorry, can you say which work did you? Can you say it again?
So active learning is the notion in machine learning where we identify some points that we're not sure of the correct label and we ask an expert to label for us. And that reminded me of the experiment you did where you used the conformal evaluation to identify points, unreliable points, where you obtained the correct label and retrain.
So yes, one point that is in the retraining experiment is that there is a phase of relabeling. So this phase we are not concerned about this relabeling phase. What we do is we identify when an object does not have a statistical support on the decision, and then of course there is another phase where an analyst needs to manually investigate this sample and needs to give a label. And we did this retraining experiment in order to confirm that the new information given as an input for a new model are actually good information, are actually a lot of information that can enrich the new model, the new classifier.
Right, okay, so my question then was, if we think of this as a technique for active learning, for identifying the samples to ask an analyst to label, in the active learning literature there are also many other techniques one could use to identify those samples, and so how do you expect this to compare to those other techniques? Do you think this is a better way to do it? Or is it just different? Are there trade-offs?
Which other techniques?
There's many techniques for active learning where you look for samples where you have low confidence on, or that are very different from any other sample you've seen, or many strategies for identifying which samples to ask an analyst to label for you.
So I think we can a bit discuss more offline on this, because I'm not sure I got this right.
Thank you.
Okay.
Okay, let's thank the speaker one more time.